Good evening, ladies and gentlemen. So sorry this is running late. I thought that I would have this done already. I've already done it once, so I'm redoing. Here we go. So what data goes with what graph? A pie graph, both words, text, numbers in the data set. The numbers, however, are percents that add up to 100, so that makes it completely and totally different from any other type of graph. So we need to be aware of that. Bar graph, it's both words and text and numbers in the data set, much like a pie graph, but instead the numbers have been measured and counted. They're not percents that add to 100. If they're percents, they're going to be percents that are less than or greater than 100. Also, the position of the words or text on that x-axis is not going to make a bit of a difference. So you don't have to worry about that because you can interpret it the same way no matter where they are. In a line graph, however, all data is in the form of numbers that have been measured and should have units of measurement. You make an xy coordinate and you plot that point in a single location. Once you've plotted your points, you create a line that runs with the trend. And this line is supposed to show how these two variables change with respect to each other. The others aren't talking about changes with respect to one another, they're just talking about changes and comparisons. This one, we're specifically talking about the changes of those two variables with one another and as that happens. Okay, 5 things that every graph should have. Should have a title, should have axes with labels and units, should have appropriate scales, should have plots of data points, and they should have either properly drawn pies, bars, or lines of best fit. So I'll explain that as we go. So for a title, the title should always reveal the IV and DV relationship, for example, volume versus mass. We do that a lot with line graphs because we have lots of IV and DV relationships there. In this particular one, we do have an IV-DV relationship. We have students, the number of students, and their favorite after-school activities. So it includes both the IV and the DV that are in the graph. For a pie graph, a little different, but same idea. We have musical styles and preferences here. Well, musical styles, well, these are the musical styles, and the preferences represent the percentages of people that like them. Here is the more traditional. This is the more traditional line, volume versus pressure. That's DV versus IV. The DV is always on the Y, the IV is always on the X. Okay, axes labels. Axes labels should always be given units when appropriate, but when numbers are counted, you don't necessarily need units. So here we go. We see numbers of students, no units, because it's numbers we've counted. Activities have no units because they're just activities. They're not even a number. Okay, here we have labels as well, but a little bit different for our pie graph. We see we have labels, alternative, classical, country, rap, rock and roll, and then we also have the labels of the percentages. That's a really good idea. It's not necessary all the time because you can see the data, but it's always a good idea to represent it that way. Okay. For a line graph, it's a little different. You have to make sure that you have something that is appropriate. See, we have pressure, and it has a unit, millimeters of mercury. We have volume, and it has a unit, centimeters cubed. So you can see how we denote that. But when we have numbers that have been measured, we have to have a unit. Okay, appropriate scale. For a bar graph, appropriate scale is only necessary for the y-axis because the x-axis, it doesn't matter. So the y-axis, you can see I have an appropriate scale. Each spot, each little mark is the same amount up and down. We don't have to worry about that. And I go by tens up to 100, which kind of makes sense. For a pie graph, the size of the pie or the angle of the pie is actually what we've plotted. So here you can see I've taken this angle right here. The way I calculated that angle, I took 360, which is the amount of degrees in a circle. I multiplied that by 0.10, and I got this angle that I then measured with a protractor. Actually, the computer did it, but you would measure with a protractor and you'd make that angle, and that's how you get the appropriate scale for the pie. Okay, for a line graph, the scale is going to matter on both the x and the y, but they do not have to be the same. In fact, you probably don't want them to be the same unless their number ranges are the same. If their number ranges aren't the same, then they definitely cannot be the same. So if we look at this one, these number ranges are not the same. Here I have numbers from 0 to 140. Here I have numbers from 0 to 60. Those number ranges aren't the same. So you can see clearly I didn't do the same scale for both of these, but the scales are appropriate. The scale on the y-axis goes up by 20 each mark. The scale on the x-axis goes over by 10 each mark. So it's appropriate, but it's not the same for each one. Okay, plot data. So for bars, we're basically telling how high does that bar need to be. That's what that's representing, the height of the bar. And so that's the plot data for a bar graph. For a pie graph, you're actually drawing that pie piece out. So you've got the angle, now draw the angle out to the edges of the circle to give yourself a pie piece. Okay? For a line graph, you're actually plotting each specific point. And you want to make that mark dark. As a matter of fact, sometimes you want to make that mark and put a circle around it, because some of you don't make those marks very dark, so that you can see that, because that becomes important later on. Okay, draw bars. So for a bar graph, we have to draw bars. So we literally draw the bar to the height that we prescribed before. For a pie graph, we define those pies. So each pie needs to be somehow defined. In this case, we're going to use color. Sometimes we can use shapes or little designs, but we want to define that a little bit so that we know that alternative is red and classical is blue and rock and roll is orange. We want to be able to see that very easily. So we have to define those pies a little bit more to give us more information. Okay, and for a line graph, we're going to draw a line of best fit. A line of best fit is just that. It's a line that fits the data. Doesn't necessarily touch all the points, but it fits the trend in the data. It could be linear, which means a straight line, or it could be a curve. It depends on what your data is saying. When you use a computer, doing a trend line option makes that job so much easier, because you don't have to worry about it. But if you don't have a computer, you can eyeball it and get an approximation that's probably pretty good. Okay, so we see, here's the trend line. Here is the line of best fit. This curve, this lighter blue curved line right here is the line of best fit. Notice it's not touching the points, which is just fine, but it fits the trend that the points are trying to make. Okay, slope. Slope is really important to us for in chemistry, because we want to use that line of best fit to tell us more information. So you can see here, I've created some sort of equation here that describes that line. So what does that mean? Well, you know more information than you think you do. So we know that when we find slope, we do slope is equal to the change in the y over the change in the x, the rise over the run. We've heard that for years. Well, in algebra, we can take that equation and change it a little bit. We can just flip some things around a little bit mathematically and get y is equal to mx plus b, which is actually exactly the same thing as the slope equation above, just rearranged a bit. Well, if we look at the equation that we got, boy, that looks like y is equal to mx plus b. Now we know what the slope of that line is. We know where it meets the y-axis, and the x value is 0. So we get a lot of information from that. And that can actually help us later if we're trying to calculate things a little bit more precisely instead of guessing. Okay, R-squared values in that line of best fit tell us how closely that line is to the line that we've created. So the closer it is to 1 or 0.1, the better that line is to the equation that you have. The further away it is, the more untrue it is. So we have to be really careful that we get high numbers. In our case, our R-squared value is 0.9986, which is very good value. So this data is very close to a straight line in the graph that we had before that we saw previously. Interpolation and extrapolation. These things seem pretty hard, but they're not. Inter means, as a prefix, means within. Extra means outside of or more than. Pola talks about the graph. So pola is a word, a Latin root that talks about the graph. So if we put the pieces together, interpolation begins to mean finding values within the data we graph. So it's amongst the pieces of data we graph. And extrapolation means finding values that are outside of the data that we graph. So let's see if we can do this. Interpolation. So first we want to find the volume at a temperature of 330 Kelvin. So we can see 330 is right here. Well, if we go up, that's within the data we graphed. There's our last point, there's our first point, and it's right smack in the middle. So how do we figure that out? Well, I draw a vertical line going up from 330 up to the line of best fit. Once I get to the line of best fit, I draw a horizontal line across where the line, that vertical line crosses the line of best fit, and I find that I see this over here, this line where it hits here. It's between 5 and 6. As a matter of fact, it's higher up than 5.5. So I'm going to call that 5.6 milliliters. It's not quite 3/4 of the way, but it's more than half. So 5.6 works really well for that. The next one, we're going to extrapolate. So let's look at this. We want to know the volume at a temperature of 250 Kelvin. So let's look at the graph again. Well, 250 is outside. It's before the first data point plotted. So this is known as extrapolation because we're outside of the data that we plotted. So we're going to be doing a similar thing, but the first thing that we need to do is a little different. I want to extend this line. So I draw another line over top of my line of best fit to extend it out. Once I've extended it out, I draw my vertical line again. Then I draw my horizontal line, and where it meets the axis, I can read it. So we can see that it's somewhere between 4 and 5. It's not quite halfway, but it's a little more than a quarter maybe. So I'm going to call that 4.3. That seems like a pretty good approximation for what I'm seeing right there. Okay, so that's interpolation and extrapolation. Direct and indirect relationships. Direct relationships mean that both variables are moving in the same direction. So when one goes up, the other goes up. When one goes down, the other goes down. So we can see the graph here that we've been looking at. As volume increases, we can see as volume is going up, so volume is going up, what's happening to temperature? Temperature is also going up. So both of these directions, going up and going right, are both going up. Going down and going left mean I'm decreasing. So we can see that this graph shows a direct relationship between temperature and volume. As temperature increases, so does volume. As temperature decreases, so does volume, and vice versa. Okay, indirect relationships are a little bit more hairy because they're a little different and we're not used to seeing them. So if we look at this graph, this is volume versus pressure. And what we notice here, as volume is decreasing, see, volume is going this way, it's going down, so volume is decreasing, but pressure is going to the right, which means it's increasing. And this is an indirect relationship because they are going in opposite directions. One is going down while the other is going up. So volume goes up, pressure goes down. So indirect relationships, we don't like them. As chemists, we don't like indirect relationships. So what we do is we change the graph a little bit, we tweak it so that we get a direct relationship. So here's a graph, the data that we just looked at in the last graph, regraphed. Notice it says volume versus 1 over pressure. This is a way that I can change some things. I do this a lot in chemistry. I find ways to give me more linear, direct relationships. And as we can see now, as volume is going up, what's happening to pressure? Pressure is going up. So as we're going up in volume, we're going right in pressure, and that's a direct relationship. Okay? You don't have to know how to do this. I just wanted to show you indirect and direct relationships and make sure you understood that. Okay? Sorry about the spelling error up there. So thank you very much for watching.